All right, graph x equals t, where also y equals t squared over 4. This is called a parametric equation. And what you do with parametric equations is it tells you what x is, it tells you what y is. So let's pick a bunch of t's and plug them in and see what it looks like in the end. So I'm going to make a table like so. I'm going to pick a bunch of t's, get a bunch of x's and a bunch of y's, and that's going to give me points to graph. I'm going to use -4 and then work my way up. So -4, -3, -2, -1, 0, 1, 2, 3, 4. Why I chose those numbers, I don't know. But I guess we'll see if it works out. If x is t, then that makes this left side pretty easy. X is t means x is -4, x is -3, x is -2, x is -1. You get the idea. You get the idea. Okay. Here the math is a little bit more complicated, but it's nothing to lose sleep over. T is -4. -4 squared is 16. Positive 16. 16 over 4 is positive 4. Okay, not bad. -3 squared is positive 9. 9 divided by 4 is 9/4, but if I'm going to graph that, I kind of want to view that as 2.25. Okay, -2 squared is 4. 4 over 4 is 1. -1 squared is 1. 1 over 4 is 1/4, so I'm going to view that as 0.25, especially since I'm going to graph it. 0 squared is 0. 0 divided by 4 is 0. 1 squared is 1. 1 over 4 is 0.25 again. 1, I already did that. 2 squared is 4. 4 over 4 is 1 again. 3 squared is 9. 9 over 4 is 2.25 again. 4 squared is a fun game, is 16. 16 over 4 is 4 again. And we see some parabola-y looking stuff. So let's graph things and label what we did as we graph them. Let's use a different color. Use purple. All right, here's my points. Here are my XY values. So you're dead to me now. So one of my points is -4, +4, and that happened when t equaled -4. Another one of my points is -3, 2.25. So -3, 2.25. So we'll sneak that there, and that happened when t was -3. Another point was -2, 1. Right here, and that happened when t was -2. Another point was -1/4, right there. That happened when t was -1. 0, 0, that happened when t was 0. 1/4 happened when t was 1. 2, 1 happened when t was 2. 3, 2.25 happened when t was 3. And last but not least, 4, 4 happened when t was 4. So here's my parabola. There it is. That looks awful. That looks better. So let's clean that up. All right. Let me see if it lets me do it. Now, the thing with parametric functions, getting ahead of myself, this is parabolic, so I didn't technically say anything wrong, is we also care about the direction from least to greatest. So we're going to put little arrows saying that this guy went that way as t got larger. Yeah. So there you go. Look at that. Look at that. Cute. Fun. Parametric equations. Let's graph this parametric equation where x is 5 sine t and y is 4 cos t, not to be confused with Ashanti, rest in peace. Whenever you graph a parametric equation, you should make a chart of t, x, y values. Now, the t's that we're going to choose, I know I'm going to choose clever ones because I'm going to eventually plug them into here and hope to take the sine and the cosine of it. So let's use all the quarters of t from 0 to pi. Maybe not even including pi. Let's just go from there. So let's start out, we're going to choose 0. We're going to choose a quarter of a pi. We're going to choose 2 quarters of a pi, so that's going to be pi over 2. We're going to choose 3 quarters of a pi, and I'm actually going to go all the way around to 2 pi because I think we should do 2 pi. I think we should do a complete circle. All right, so I'll plug in pi, I'll plug in 5 quarters of a pi, I'll plug in, what's next? 3 pi over 2. I'll plug in 7 pi over 4. And that should get me where I need to be. All right. I'm just letting you know ahead of time, I'm using a calculator for all this. So when I use these numbers, when I plug in 5 sine t, I'm plugging in 5 sine 0, which gets me 0. When I plug 5 sine pi over 4, that gets me 3.5. It gets me a much worse number than that. But again, if I'm going to just graph on here, it really doesn't matter what the exact numbers are as long as I'm graphing for accuracy. When I plug in pi over 2, I get 5 because sine of pi over 2 is 1. 5 times that is 5. When I plug this in, I get 3.5 again. When I plug in pi, I get 0 because sine of pi is 0. When I plug this in, I get negative 3.5. When I plug in 3 pi over 2, I get negative 5. And when I plug in 7 pi over 4, I get negative 3.5. So those are my x values. Okay, here, here, here. It's just everywhere. I'm going to plug these into the y function. I'm again using my calculator. I'm going to get terrible numbers and then just simplify it to, or round it rather, to the nearest tenth. When I plug in 0, I end up with 4 because cos 0 is 1. 1 times 4 is 4. When I plug in pi over 4, I end up with 2.8, which is a much worse number. But again, I'm not going to lose sleep over that. Cosine of pi over 2 is 0, so 4 times it is also 0. When I plug in 3 pi over 4, multiply it by 4, I get negative 2.8. When I plug in pi, I get negative 1. 4 times that is negative 4. When I plug this in, multiply it to 4, I get negative pi, or negative 2.8 rather. Plug in regular 3 pi over 2, I get 0. And when I plug in 7 pi over 2, I get 2.8. Gross. All right. Let's graph these. And as I graph them, I'm going to say where my t was. So 0, 4 lives around here. T was 0 for this one. 3.5 lives here-ish. 2.8 lives here-ish. And t was pi over 4 for that one. Okay, the next point is 5, 0. And that was t is pi over 2. The next point is 3.5, negative 2.8. So like right around there. That's when t was 3 pi over 4. What's the next one? 0, negative 4. that's when t was pi. Negative 3.5, negative 3.5 right around there, negative 2.8 right around there. That's when t was 5 pi over 4. Negative 5, 0, negative 5, 0. That's when t was 3 pi over 2. And negative 3.5 lives right around there, up 2.8 lives right around there. That's when t was 7 pi over 4. So we got ourselves kind of like an oval-looking thing, an ellipse. Okay? So I'm going to try my best to draw this the best that I can. After I draw it, I'll get an oval ellipsy looking thing. And of course, we always include the directions that we go in. And again, if you're like, well, why did you stop at this number and not go to 2 pi? Because 0 is 2 pi, and why repeat myself? And as you can see, it kind of goes around in a circle. Circular, circle. What's a movie? I forget which one. I think it's Billy Madison. Like and subscribe. A soccer ball is kicked across a field at an angle of 30 degrees with an initial speed of 16 meters per second. Write a set of parametric equations for the motion of the soccer ball. All right, generally speaking, parametric equations are x equals stuff, y equals stuff. There's a rule that says if you're dealing with initial speed problems, the x equation is going to be the initial speed times cosine theta times t, and y is going to be completely based off of like the gravity function, which is negative 16t squared plus the initial speed sine theta t. If I started at a specific height, I would add h, but I'm not doing that here. My x value is going to be the initial speed, which is 16, cos theta, which is 30 degrees. All of that times t. I'm going to take this guy, figure out what this is. So let me see. Cos theta is root 3 over 2. I have to think about that for a second. 16 over 2 is going to be 8. So 8 root 3 t is going to be my guy. Some people might want you to say 8t root 3, but I'm not going to lose sleep over that. This guy, a little more involved, but not the end of the world. Y is going to equal negative 16t squared plus my initial speed, which is 16 again, sine theta, which is going to be sine 30 degrees. Again, t is attached. Sine 30 degrees is a half. So y is going to equal negative 16t squared plus 16 times a half times t, which ends up simplifying out to negative 16 t squared plus 8t. Those are my parametric equations. Fun. Graph each polar coordinate. When you graph a polar coordinate, the first number that you see tells you the length, like a radius. And the second one tells you where around your polar plane, try saying that fast, you're going to end up putting your point. So this guy is basically saying my point is going to be 3 units away from the center, and I'm going to place that at 150. So where's 150? There you is. 1, 2, 3. That's going to be my first point that I'm going to make in blue. The second guy that I'm going to make in green is going to be 2 units away, but it's going to happen at negative 255. Well, what's negative 255? I don't know. So let's add 360 to it to spin it around. When I add 360 to it, that changes this to 105 degrees. So I look for 105 degrees. That's halfway in between 90 and 20. I'm going to put a dot that's 2 units away, and that's going to be that point right there. All right, so that's how you graph polar coordinates when given degrees. Not so bad. Let's graph polar coordinates in radians. Oh, I can barely contain myself. Polar bear? So the first number in a polar coordinate tells you how far away from the origin your point is going to go. This tells you where on the polar axis you're going to put your polar coordinate. 11 pi over 6, you might be looking at this and saying, oh, there you are. 3 is going to be, what, 1, 2, 3 units away. So right there, yep, it's as simple as that. So that's your first one. And I'll make you red. Now, -3, kind of weird. You're like, you can't make something -3 away. Sure you can. That's just going to mean backwards. Yeah, backwards. All right, so first let's find out where 23 pi over 12 is. Well, there's no 23 pi over 12. But if you think logically, 23 pi over 12 would be right here, if you think logically. So if it's going to be 1, 2, 3, that's where I would put my dot. But since this is going to be negative, it's going to be 1, 2, 3, which is going to live right there. Okay? So that's how you graph polar coordinates in radians. Super cool. Because it's polar. Polar means cold. Like and subscribe. Find the distance between these two polar coordinates right here. All right, before we do too much, let's try to draw these out in a very, 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 very basic way. So I'm drawing myself a polar plane, not pretty at all. There's pi, there's 0, yada, 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 yada. Pi over 3 would be somewhere around here. So let's just say that, this is 2. They're both 2, so that makes life a little easy. But you're going to be 2 pi over 3. So this measurement is pi over 3 degrees away, in radians rather, radians away from 0. Not too hard to understand. This guy is going to exist at 11 pi over 6, which is somewhere over here. Now, 11 pi over 6, if this is 11 pi over 6, implies that this is 1 pi over 6 units away from 0. So if I want to find this distance, what I'm looking at is I'm looking at a triangle where I need to find out what this angle is right here. So pi over 3 plus pi over 6 means I could change that into 2 pi over 6, 2 pi over 6 plus 1 pi over 6 plus is a cool 3 pi over 6 or pi over 2. So you are pi over 2. I know that you're 2, and I know that you're 2. So what I'm going to do is I'm going to bring back an old friend, and that old friend says, how can you find an opposite side if I give you an angle and I give you 2 sides? Well, that would be the law of cosines, of course. Law of cosines, c squared equals a squared plus b squared minus 2ab cos c. What do I know? I know that I need to find c. C squared equals 2 squared plus 2 squared minus 2 times 2 times 2 times cos pi over 2. Here's a nice thing. Cos pi over 2 is 0. You go away. So c squared is equal to 4 plus 4, which is 8. square root both sides, and c is going to equal 2 times 2 times 2, 2 root 2. So some of you might have noticed right off the bat, isn't pi over 2 90 degrees? Yeah. So isn't this a right triangle? Yeah. So couldn't have used Pythagorean theorem? Yeah. But I didn't because I just wanted to show you law of cosines anyway because it's fun. All these two twos, where am I, at a ballet recital? Graph r equals 6 sine 3 theta, where theta is in between 0 and pi. Polar graphs are gorgeous. They're the most beautiful graphs that you see in math. They're also a nightmare to create. And the reason why they're a nightmare to create is because you have to put all these points all over the place, but when you finally connect things together, it just looks so very good. So what I'm going to do is I'm going to use these bounds right here between 0 and pi, whatever that is. I'm going to use every single one of these numbers right here so I can get myself as complete of a graph as possible. Now, just a heads up, I am going to use a calculator to get my numbers. You could do this without a calculator. It's possible, but I don't have a death wish, and so I'm not going to do it. Now, what I'm going to do is plug in all these thetas. What I'm not going to do is plug that right into a graphing calculator and try to trace this out, whatever it is. I'm going to be accurate but cheat a little bit, just a little bit. So I'm going to use all of these values from between 0 and pi and see what happens. So I'm going to plug in. I actually might need 2 rows of this. I actually might need 2 graphs. So let me make another one. All right. So I'm going to plug in 0. I'm going to plug in pi over 12. I'm going to plug in pi over 6. I'm going to plug in pi over 4. I'm going to plug in pi over 3. I'm going to plug in 5 pi over 12 and pi over 2. Like that. And then when I'm done that, I'm going to also plug in 7 pi over 12. I'm going to plug in 12. I did that right. I'm going to plug in 2 pi over 3. I'm going to plug in 3 pi over 4. I'm going to plug in pi over 11 pi over 12, and just to have some fun, I'm going to plug in pi, even though I'm not supposed to. I'm doing it anyway. You can't stop me. So when I plug these into a graphing calculator or a scientific calculator or whatever, I'm not going to worry too much about the square roots and the blahs. I'm just going to do it. All right. Sine of 0 is 0, so this becomes 0. This becomes 4.2 when I plug all that into my calculator. U becomes 6. Oh, look, 4.2 again. How about that? I wonder if that's going to continue being a pattern. I don't know. I guess we'll find out. U becomes 0. And you become, oh, weird, negative 4.2. How strange how all of this repeats. U become negative 6. Let me switch my color. U becomes 7 pi over 2, negative 4.2. U becomes 0, U become 4.2, U become 6, U become 4.2, and U, even though you don't really matter, becomes 0. Now, the fun part about this is graphing all those points and making sure you don't screw up. So let's do that. 0, 0 means I start at 0 and I haven't moved anywhere. Okay, I can handle that. Pi over 12 is this guy. 4.2 is going to be like here, so I'll put a dot like right there. Pi over 6, 6 is going to be that guy right there. The next one up, pi over 4, is going to be 4.2. What's next? Pi over 3 is going to be 0 again. Okay. 5 pi over 12 is going to be negative 4.2. So if regular 4.2 would be here, then I'm going to follow the line and make sure it's at negative 4.2, which is that guy right there. Half a pi is going to be negative 6. So negative 6 is that dot. Here we are on this one. 7 pi over 2 is going to be negative 4.2. So that guy right there. 3/4 of a pi over 4 is, I forgot one. 2 pi over 3 is going to be 0. So that one right there. 2 pi over 3 is going to be 0. So again, I'm repeating myself. 5 pi, or no, I missed one. 3/4 of a pi is going to be 4.2 in the positive range. And so where was 4? There was 4, 3/4 of a pi, 4.2. Then 5 pi over 6 is going to be 6, so u. And then 11 pi over 12 is going to be 4.2. And back to 0, not that it even matters. So now I need to find a way to draw this, and this is where I'm afraid I'm going to fail, but we'll see what happens. Okay, this is a pretty looking thing. Now you see that I'm trying to make the motions of it. Okay, this is a polar graph that's going to start at 0, 0, make this pretty little loop there. Okay, keep coming down. Keep dumbing down. Oh, Dr. Freud. That actually looks really good. And then come over here. And there you go. This creates what's called a rose, or as Rick Ross would say, rosé, because he's a rapper. I don't know what it means, but, he said it, so that's how you graph a polar graph. Pretty cool stuff. Pretty fun stuff. Pretty beautiful stuff. I like it. Convert from polar to rectangular form. We know what polar is. Polar turns these things into pretty little roses and hearts and stuff like that. Well, rectangular form is just the regular y equals blah, blah, blah. In order to do that, what we have to do is we have to use these three things. We have to say that x equals r cos theta. That's thing number one. We have to say that y equals r sine theta. It's supposed to be an n. That's thing number two. And we have to say that r squared equals x squared plus y squared. So in order for us to make this look like stuff with x's and y's, first thing we need to do is why don't we turn that r into r squared? Let's multiply it by r. If I multiply the left by r, I have to multiply the right by r. So the left is now r squared, and we'll change that in a little bit. Distributive property puts that r right after the 4. So 4, oh, look at that, r cos theta. Minus r times 4. Oh, r sine theta. Now we have enough information where we can start swapping things around. R squared is now x squared plus y squared. R cos theta is now x. R sine theta is now y. Now, maybe we could leave it like this, and maybe some teachers would be happy with this, but I'm not really happy with this. I'm not happy at all. What I want to do is I want to make it look a lot prettier. So I'm going to move everything to the left. I'm going to subtract 4x from both sides, minus 4x, and I'm going to add 4y to both sides, plus 4y. Let me get some colors out here. That gets me x squared minus 4x, leave some space, y squared plus 4y, leave some space, equals 0. Now, what I want to do is I want to make this look like something squared, x something squared. And I want to do the same thing with that. My goodness gracious. I want to do the same thing with that, but with a y squared. How do I do that? Well, difference of squares, of course. Take half of this number, square it, and add it to both sides. So half of 4 is negative 2. Square that is positive 4. So let's add 4 to both sides. Same thing over here. This is supposed to have a y attached to it, and I simply forgot. Same thing over here. Take half of 4, 2, square that 4, and add 4 to both sides. What we have here is we have a perfect square trinomial that factors out to x minus 2 squared. Oh, what do we have here? A perfect square trinomial that factors out to y plus 2 squared. And what do we have over here? 8. So now it's in rectangular form, and it's a pretty version of rectangular form. That's what I like. That's what I want. And that's what I'm sticking with. Let's graph this point on the imaginary plane. So I is a real number. 3 has the imaginary number complex. So go right 1, go up 3. Thanks for watching. Like and subscribe. Simplify 4 plus 4i, 5 minus 3i, FOIL, and imaginary numbers. I love imaginary numbers. You know that imaginary number is the square root of negative 1. But there's also some repetition going on here. I squared means I would be allowed to square a square root, which just gets me negative 1. I to the third, if I ever come to that, would be negative 1 times I, so negative I. And I to the fourth would be this guy to the fourth power, which is 1. And then everything just repeats itself. So what I'm going to do is I'm going to FOIL. So 4 times 5 is 20. 4 times negative 3i is negative 12i. 4i times 5 is 20i. And 4i times negative 3i is negative 12i squared. Let's turn any of these I squareds, I cubes, or I to the fourths into something different. And while we're at it, let's combine these guys. So you become 20 still. You simplify to 8i. And negative 12i squared becomes negative 12 times negative 1. Negative 12 times negative 1 is 12. 12 plus 20 is 32. 32 plus 8i is my simplified version of that FOILed problem. Now it's a complex number, and it's a pretty complex number. All right, my job is to simplify 6 minus 2i, 2 plus 4i. And you might be looking at this and thinking, well, okay, there's a 2 in common, so let's take care of that. So let's bring out a 2. That's 3 minus I over 2. That's 1 plus 2i. Cross you out, and you now have 3 minus I over 1 plus 2i. And you might look at that and be like, done. We're not done. There's an issue here. I is the square root of negative 1. And last time I checked, you can't have square roots in the denominator of a fraction. So the way we're going to handle this is we're going to multiply the top and the bottom by what's called the conjugate. This is basically a difference of squares problem that eliminates all possibilities of having square roots or i's on the bottom. So the conjugate is whatever the bottom is, but flip the middle symbol. So 1 minus 2i, 1 minus 2i, multiply the top and the bottom by that. So we have a FOIL problem upstairs. We have a FOIL problem downstairs. But the FOIL problem downstairs is going to make us happy. Upstairs we have 3 times 1. We have 3 times negative 2i, so minus 6i. We have negative 1 times I, so negative I. And we have negative 1, or negative I times negative 2i, which is positive 2i squared. That's going to be all over. 1 times 1, which is 1. Minus 2i plus 2i disappears. That's supposed to happen. Minus 4i squared. So let's combine the two like terms upstairs in the numerator. So 3 doesn't change yet. This becomes negative 7i. And 2i squared, remember, I squared is the same thing as negative 1. So 2i squared is the same thing as 2 times negative 1, which is the same thing as negative 2. So that'll simplify. Similarly, on the bottom, we have 4i squared, which is the same thing as 4 times negative 1. So that becomes plus 4. On the top, these combine to 1. So 1 plus 7i. On the bottom, this just turns into a 5. And some teachers want you to split this up and say this is 1/5 plus 7 over 5i. So now it's in the appropriate imaginary complex form. But that's our guy. Now I, or a square root, is no longer in the denominator. Everything's the way it should be, and that's my answer. Negative 1 minus 6i cubed. All right, let's write this all out. Negative 1 minus 6i, negative 1 minus 6i, negative 1 minus 6i. Let's remind ourselves that I is just I, this negative 1 inside of a square root. I squared turns into negative 1. I cubed turns into negative I. I don't think we're going to have to deal with any more than that. Let's FOIL. I know some of you might be like, well, can't we use some kind of shortcut? We can, but I won't because I don't have everything memorized. Negative 1 times negative 1 is going to be positive 1. Negative 1 times negative 6i is going to be positive 6i. Positive 6i again. Positive 36i squared. I'll change that in a little bit. That's going to be multiplied to negative 1 minus 6i. These two combine to make 12i. While I'm at it, 1 plus 36i squared combines because I squared is negative 1. So I squared becomes negative 1, which makes this negative 36. 1 minus 36 is negative 35. So negative 35 plus 12i times negative 1 minus 6i. Let's FOIL again. 35 plus 210i minus 12i minus 72i squared? Yes, 72i squared. Let's combine these. That becomes 208i. Nope, just kidding. 198i. That becomes plus 72 and 75. Oh my gosh, 35 plus 72 is 107. Now it's in complex form. Now it's completely simplified. Now it's beautiful. The end.